Hi all, thanks for coming to this seminar. This is Jose Carbonell from PerMedCoE. My talk is about a recently created center of excellence that focus on personalized medicine, but from an HPC point of view, because one of the main objectives that we have here in this project is to refactor a set of essential tools to increase their performance in professional environments, like for instance, the Mare-Nostrum supercomputer. So I'm going to start the talk by giving an overview of the project, who is involved in this project, and what are the main pieces that we have. So in this case, we are several institutions from several parts of Europe. We have different backgrounds. We have institutions like, for instance, Personal Supercomputing Center or the CSE Institute that are more involved in those computational goals that we have in the project, but we also have other institutions like, for instance, based in Korea, that are more related with the molecular biology objectives that we have in the use cases that are included. In this case, we also have Atos as a company in order to have a link with the industry, because we want to have a sustainable project that could engage also this part of the society. So this part has three main pieces. The first one is the cell level simulations, because the main objective of the project is to create multi-scale simulations where we simulate cells interacting in a tissue, or for instance in a tumor mass. So in this case, what we want also in the project is to combine these cell level simulations with other core tools or other essential tools that are usually employed by the user community to model molecular pathways or to simulate the behavior of molecular pathways. The idea is to combine these two categories of tools in order to provide, or in order to have more realistic behavior of the cells that are being simulated in a multi-scale simulation. Of course, the third part of this project that is very, very important is to take these two categories of tools and to combine them and to refactor them in order to increase their performance and scalability into HPC environments or professional supercomputers, because the idea is to increase the complexity of the simulations. The idea is to be very close to real scenarios, like, for instance, a tumor growing, or for instance, a piece of a patient's tissue. And in this case, what we will need in the future is to increase the number of cells that we have in these kind of situations, in these kind of simulations, or for instance, to include more complex pathways, or including, for instance, the signaling pathways and metabolic pathways. So at the end, if we want to have all this complexity in order to have a realistic behavior, what we need is to take these essential tools and to improve them in order to be able to run in different computers, or to run even across different machines in different supercomputers. So these are the main pieces of PerMedCoE. So we started with a clear motivation. First of all, the simulation of cellular mechanistic models are essential for future paradigms, like, for instance, personalized medicine or drug design. In this case, it's not only a matter of doing an analysis, modeling molecular pathways. We also want to simulate the tissue, to simulate the cells interacting, and also interacting with different substrates that we have at the cellular space. And we also know that the performance of these tools is limited due to the resources that we have in a single machine. And in this case, we want to have, as I mentioned before, we want to have realistic simulations. We will need to increase these resources to run, for instance, a single large simulation. So in order to success in these goals, what we want is to create a sustainable roadmap to scale up these essential tools that we are selecting. Of course, to have a roadmap that could be sustainable, because the idea is to create a user community around PerMedCoE in order to work in personalized medicine and also in HPC environments. And of course, the idea is to have actionable models that could be used in a daily clinic, that even people that are not particularly advanced, that have no particular advanced skills in computation could use, or could have an open door to use a HPC environment by using our tools to have these kind of patient-specific models or cell type-specific models in order to provide like a a relevant change in the paradigm of personalized medicine. So we have several steps, we have several pieces in this project. Of course, the first one is to start optimizing these essential tools that we are selecting, but also we have to select specifically use cases that could illustrate properly the development that we are doing. The idea is to have these tools and to let the user community to use them and to create new models and to use it to new use cases. And also to build this sustainable project in order to even to train different biomedical professionals, not only those who are more close to computational biology, but also some others that are more related with the daily clinic, or maybe those other professionals that are more related to molecular biology institutes. So these are different points in our road that we have to complete. Of course, this is a kind of cycle, because in the future what we want is to start including more tools, more essential tools, in order to create a more rich catalog of different analysis. And in order to do this, we, as I mentioned before, we have a set of selected core tools. In this case, we started with 4 selected core tools. The first one is PhysiCell, that is the tool that we use in order to do the multi-scale level simulations. PhysiCell, it's a powerful tool, a powerful library of code that could be used in order to create realistic simulations. But also we included 3 different tools. We included Cobra Toolbox, that is a very popular tool that is very useful in order to model the metabolism, the metabolic network, but also included CellNob, that focuses in the inference or in the modeling of signal transduction networks. And also we included Mabos, that is a tool that is able to model and to explore and to analyze different Boolean models that could represent, for instance, also a signal transduction network, or for instance, a differentiation lineage of cells. In this case, these 4 tools are going to be refactored by our project, but we also want to include the experience of other centers of excellence, in particular the POP Center of Excellence, in order to guide this refactoring of the tools, in order to identify the different bottlenecks that we have in our tools, because the idea is to take advantage of all the resources that a single machine has when we run a single simulation in one machine, but we also want to run these tools in different machines. So we have like a combination of different protocols of different methodologies, and it's very important to identify these bottlenecks that at the end are those useful changes that provide this dramatic increase in the scalability of the tools. So in order to do this, we will take into account all the considerations of the BSc, the experts that are at the BSc, and also included in the POP Center of Excellence. And in this case, those tools, those core tools, have been selected because they are essential tools that are widely used by the user community. The first one, as I mentioned before, is PhysiCell, the tool that we use to perform the cell level simulation. PhysiCell is a physics-based virtual microscope. It's a kind of virtual cell culture that we can simulate. It implements an agent-based paradigm in order to define the individual behavior of every single cell that is included in a given simulation. And PhysiCell provides a bunch of different functions in order to model the cell phenotype. So we can model the cell growth, we can model the cell division, we can define when the cell undergoes apoptosis, for instance. But we also could model the different physical interaction that we have between adjacent cells. But we also could model, for instance, the interaction that the cell have by using different substrates that are secreted at or from the extracellular space. And in this case, in order to do this, PhysiCell is based on a diffusion transport solver. It's based on differential equations. And what PhysiCell is able to do is to model the concentration of different substrates across the cellular space. By using this kind of function, this kind of pieces, we can model realistic biological use cases. Like, for instance, we can recapitulate the necrotic code that we found in a spheroid of cells due to the limited amount of oxygen. We can model different things in this case. For instance, we also can model like the secretion of different substrate by the tumor cells in order to promote the creation of a new vascular system. And this is a powerful tool that we want to refract, or we want to explore in order to succeed with this project. Apart from this tool, we also want to have Cobra. Cobra is a very popular framework that have many different implementations in different programming languages, for instance, in MATLAB, in Python. And this framework is useful to infer metabolic networks and also to do those most popular kind of analysis, like, for instance, flux balance analysis or flux variability analysis. We also have MABOS, as mentioned before, in order to model the stochastic model of Boolean networks. MABOS is based on a continuous time Markov process. MABOS uses transition rates in order to expand the purely Boolean networks in order to model the probability that a certain protein is activating another one. And in this case, MABOS, by using like a very simple language, with MABOS you can model different networks or different contexts, different cellular contexts. And in this case, you can use this tool in order, for instance, to understand or to evaluate, for instance, a Boolean network that is representing the mammalian cell cycle or many other different contexts. In this case, MABOS provides like a stochastic framework to model the different states that a Boolean network can have, and the idea is to evaluate or to determine for a given Boolean model, to determine what are those steady stages or those attractors that could be captured by performing hundreds or thousands of different executions and to evaluating what are those main final stages in the Boolean network. So we also have in the project CellNob. CellNob is a tool that is based on logic-based models to model signal transduction. CellNob is useful to model signaling networks. In this case, CellNob starts with a PKN network that is representing like those possible interactions that you can have in your cellular context or in your cell type or in your tissue. And by using different formalism, CellNob is able to infer the signaling networks and then to simulate new data or to model more or less the behavior in order to mimic the real data that you can have. CellNob is mainly using phosphoproteomics. A natural extension of CellNob that is also included in the CellNob ecosystem is Carnival. Carnival tries to take RNA-seq data or transcriptomics data, and then to infer the signaling networks that are active in a given context. In this case, Carnival is using some other tools that are included in this ecosystem. One of them is OmniPath. It is a huge database integrating different interactions from different databases. It's like a compilation of many different databases. And also we use the Orfea, that is like a database including all the possible relations between transcription factor and their targets. And also in this case, Carnival is using programming in order to estimate activity of a selected group of pathways. By combining these tools, Carnival is useful to predict the signaling networks, and at the core of this tool, what we have is an integral linear programming solver. This is one of the main objectives that we have in our project, because the integral linear programming optimizer could be included in different tools, and are very useful tools that could be even explored to many different projects. So in our project, we not only want to refactor the tools or to build different building blocks, but we also want to combine different pieces to form a catalog of different workflows that could be useful for the community of end users. In this case, we think that our core tools combined with other pieces of interest could be useful in order to cover many different use cases and many different scenarios. The idea is not only to include building blocks corresponding to core tools, but also to include some other building blocks that correspond, for instance, to single cell data processing packages or some other pieces that could be included in order to connect the different core tools with our tools in order to create a rich use case. Of course, in order to do this, having the example of other center of excellence, like for instance BioExcel, what wants to take the core tools and some other packages and to create containers, to create similarity containers or Docker containers, and to combine them by using different workflow managers, like for instance COMS or PyCOMS, that is being developed at the BSc, or maybe other solutions like Nextflow. So by using this combination of containers and workflow managers, we want to create realistic workflows. This is an example. This is a pilot workflow that we are developing. This is the first workflow that we are developing. And in this case, what we have is a combination of different tools. The idea here, this is a COVID-19 related use case. In this case, the idea is to create patient-specific models in order to create some variable of interest, like for instance the outcome of the patient or the degree of let's say infection that we have for the virus. To start this workflow, we need to process, or in this case, we are using single cell data, so we need a building block processing the single cell data for every single patient. But also by implementing or in this case, in this pilot workflow, we need a Boolean model. In this case, probably will be used a Boolean model from the disease maps community. This Boolean model, for instance, could represent a cell cycle model, for instance, or a Boolean model that is represented the decision that the cell should take in order to undergo apoptosis, for instance, or to undergo cell cycle. And for instance, in this case, we use MAVOS in order to analyze this Boolean network and to find a set of possible gene candidates in order to evaluate if knocking down or knocking out some genes we can force the apoptosis of the epithelial cells that are infected. By using these gene candidates, we can perform a patient-specific model by doing many different simulations, by doing hundreds of simulations, evaluating how is for instance, what is the effect of knocking down a single gene, but also by combining different genes to create like some kind of epistasis in order to evaluate if there are a combination of genes that are more useful in order to stop the infection. In this case, for instance, we have several possibilities to distribute the working among different machines. We have we can evaluate different gene candidates that corresponds to executions of MAVOS, for instance, or execution of other core tools in different machines. But we also have a patient-specific model, so we can distribute the different analysis for the different patients across different machines. So this is something that we want to work on, that we want to have very clear how to parallelize the code in order to have very efficient use cases, very efficient workflows combined by composed of different building blocks. So what are the main refactoring strategies that we are following in our project? The first one is the use of Julia. Julia is a dynamic programming language. It's a programming language that natively supports concurrency. It supports both distributed and parallel computing. So this is an ideal programming language to work in an HPC environment. In this case, we are starting, or we are working in a Julia package of some of the analysis that are included in the Cobra toolbox. The name of this package is Corexa, and this is one of the main strategies that we are following in order to refactor this kind of tools. In this case, by using Corexa, you can work with very large metabolic models, because we take advantage of the Julia capabilities. And also, for instance, you want to test many different variants, you want to test hundreds of thousands of different variants in this metabolic network. This is a very useful tool. A second approximation that we are following is to do a benchmarking of different linear programming solvers or integral linear programming solvers, because in particular at the core of Carbonell and also one of the flavors that we have for 7-ops, they use integral linear programming. So in particular, we are testing different integral linear programming solvers that we are very interested in to integrate GuruB, that is a very useful solver, and this solver could be has the possibility to run among different computers. So at the end, it's a kind of interesting refactoring strategy, because what we are doing is to take one piece that is at the core of the tool, and we are trying to refactor this or to modify this piece in order to be able to run among different computers. So other strategy that is very, very important in our case is the use of MPI. MPI is a very popular protocol in order to run a single tool across different machines. So the natural scenario is the distributed computing, of course, but MPI could also be combined with other protocols or with other paradigms, like, for instance, OpenMP, in order to take advantage of all the resources that a single machine has. So in this case, this is a protocol that we want to use in different tools. We want to refactor PhysiCell. We want to refactor also 7-op by using MPI, and it is not only useful in order to run a single execution among different machines, but also to combine all the resources of these machines that are being executing the code, executing the tool, but also to combine these resources as a single large machine. This is a very important point, because in our case, as I mentioned before, what we want is to create or to simulate more complex scenarios by not only using, for instance, thousands of cells, that is the usual case right now, but also to perform simulations with millions of cells. And in order to do this, we have to mimic, we need to have like something very similar to a very large machine, combining the resources of not only many different machines, but also many different, for instance, supercomputers. So this is a particular case of PhysiCell MPI. In this case, the main strategy that we are following to refactor PhysiCell is to divide the cellular space in different subdomains. And in this case, the MPI messages that the different nodes should send among them are related with those cells that are crossing one subdomain to other subdomain. This is very important because in general the cells are moving across in a realistic simulation. So we have to implement something that could be very accurate and very stable and very useful in order to have this kind of huge simulations. So other interesting approximation that we are following is the combination of PhysiCell with the rest of core tools. In this case, we have started with the PhysiBoss tool, that is the combination of PhysiCell with MABOS. In this case, this tool recapitulates one of the main novelties that I mentioned at the beginning of my talk this day, the combination of the inclusion of those tools that are useful to model molecular pathway into every single agent that represents the behavior of a single cell in the simulation. In this case, MABOS uses Boolean models. By using this tool, we can model many different situations. For instance, we can model the effect of a given drug or of a given treatment, not only a static treatment, but also we can model different dynamics. For instance, we can model different pulses of treatments and to evaluate if this treatment affect the number of cells that undergo apoptosis, for instance, or the number of cells that are being proliferating. But also we can model different, for instance, heterogeneous cell populations, including those wild type cells, but also included in the same cell population some other cells that could include some knockouts in order to evaluate how the knockout of a given gene is affecting the, for instance, the number of tumoral cells if we are simulating a tumor, or the number of cells that are being divided. So of course, these core tools are being combined in order to perform use cases. We have a selection of 5 use cases. In this case, we initially selected 4 use cases, but we decided to add a new one because of the pandemic situation. The first use case is about cancer diagnosis based on all different omics information. We are focusing on chronic lymphocytic leukemia, and the idea is to create patient-specific models to develop simulations or ensembles of simulations that could be useful in order to predict different clinical variables of interest that we have for those patients. For instance, the survival, or to evaluate if the simulations could recapitulate the different subtypes that we have in the disease. We also have a use case about drug synergies. In this case, we will take some data that we have, some experimental data in cancer cell lines, and the idea is to evaluate our tools, to evaluate our cell simulation tools in order to understand if we can predict for specific cell lines, we can predict the synergy of some drugs that do not show this kind of synergy in all the cell types. So we also included, as I mentioned, the COVID-19 use case, and also at the beginning we have a use case centered in rare diseases. And also we have a 5th use case that tries, by using single cell data, single cell omics, and by using images, what we want in this case, in this use case, is to simulate the evolution of, or the growth of a tumor. In this case, we are really interested in to simulate the inclusion of different clones in the tumor, and to evaluate how the knockout of different genes could affect to the survival of those clones, and at the end to have a system that could be useful in order to recapitulate the selective pressures that one can show in a real tumor. So in the case of the use case of COVID-19, that is a use case that we have more advanced because of the pandemic situation. What we are doing in this case is to take some molecular pathways, some models that have been collected by the disease maps community, in particular by the team that is around COVID-19 disease. And we also take a community-driven initiative by Paul McLean, that is the main developer of TCL. And in this case, what we are doing is to take like a very interesting model, including epithelial cells that are being infected by the virus, and also including some immune cells that are fighting against the virus. But also they are producing this cytokine storm in the disease, and also including some other factors that could be interesting in order to have a realistic simulation describing the COVID-19, the SARS-CoV-2 infection in a real disease. In this case, the virus is modeled as a substrate in the simulation, and the epithelial cells are the host cells that is being infected. And as I mentioned, by using Boolean model, we want to evaluate this. In this case, what we did is to take this pathway that is included in this map community to create. We use a tool that is called Cascade in order to obtain a Boolean model. And by using this Boolean model, what we did is to use physibus in order to evaluate different scenarios. In particular, we were interested in to understand how different mutants or different mutations could affect the apoptosis of those epithelial cells that are being infected. Of course, by using this model is very useful in order to evaluate how is the effect of having a different population of cells that are quite heterogeneous, or modulating different effects like the inclusion of more immune cells. So thank you very much. This is all from my side. If you are interested in the project, you have questions or whatever, of course, don't hesitate to contact me or to contact the project. Thank you very much for being here in this talk.